All right, so today's lesson is on the types of solids. All right, and then after this, I'm going to get into vapor pressure and stuff like that. But let's first talk about the different types of solids and their properties and stuff like that. I've lost my pen. There it is. Does anyone know where it is? Lost my mind. Okay, so I'm actually going to fill in this chart from the right to the left. I know. Sorry, Will. You've been referenced on the video. Alrighty, so I'm going to start with ionic solids. All right. So another name for an ionic solid is a salt. Anything that's not an acid or a base is an ionic salt. All right, so what would be an example of an ionic solid? That's always an example that people give, NaCl. Can you give me one a little bit better? CaCl2 works. Can you give me one a little more complex? Wow. You would think it's Monday by your, responses. I know it's Tuesday, but it is kind of like the Monday of the week. What? CrO4 would be part of it, because that's but maybe let's get one with a polyatomic ion.
NaNO3.
How about like potassium dichromate? Let's get some real. I don't believe you. I don't believe that you were about to say that. All right, so the type of bonding, so what's holding these molecules together is electrostatic attraction. Okay, it's a crystal lattice, all right? And there's actually, based on the ionic compound, there's different types of lattice structures. There's like center cubic and all this stuff. We're not gonna get into all that. If you wanna do stuff like that, take a class in college on that, but it's a crystalline lattice. All right. Typical properties of ionic solids are going to be high melting and boiling points. High melting, boiling points. These are brittle. The actual lattice is brittle, but the bonds themselves that are holding the two ions or two or three or whatever ions together are very strong. Okay, and I'll talk a little bit more about that when we talk about some covalent network stuff. Okay. Alrighty. Yeah, MP/BP, melting point, boiling point. Molecular solids. Molecular solids. So these are going to be our covalent compounds. All right, our covalent compounds. The lone atoms are going to be the lone atoms based off of the name, right? So what would be an example of a solid that's a covalent compound? It might not have to be solid at room temperature. It just can maybe become a solid. CO2, yay! Does anyone know what solid CO2 is called? Dry ice. That's dry ice. Anything? There we go, thank you. I was about to grab my water bottle. Water. You may have experienced solid water at some point in your life. Apparently it was falling from the sky yesterday. It is April 10th. Okay, so yeah, molecular nonmetals. What's holding these molecules together? Dipole-dipole, hydrogen bonding, London dispersion forces. All together they're called intermolecular forces, or we could say van der Waals forces. All right, intermolecular forces. All right, so typical properties. These are actually going to vary depending on the strength of the intermolecular force. For example, the boiling point of water is very, very high compared to that of carbon dioxide. So it really just depends on the strength of that intermolecular force. All right, so it varies depending on IMF strength. Wonderful. I want purple. All right, lone atoms. Lone atoms. Now, the lone atoms here, do you notice how under atomic we have covalent network, metallic, and then lone atoms? So the metallic ones are going to be the metallic lone atoms, and then the lone atoms, these are going to be our non-metal lone atoms, and these will be the metallic lone atoms. Well, I don't want to put lone atoms with metallic because there's a couple other examples that aren't lone atoms, but they're all metallic atoms. So what would be an example of a non-metal lone atom? Carbon's a great guess, and you would think you'd be right, but that actually is going to go under covalent network, and it's really special, so we're not going to put carbon down for a non-metal lone atom. But bromine, if bromine was in the solid form, yeah, diatomics would count as lone atoms as long as they're in the solid form. What about, sulfur? Sulfur or phosphorus, okay? Anything that's a non-metal other than carbon and silicon, because they're special. Just those two. All right. All right, type of bonding or intermolecular attraction. There's only one type of force that holds these molecules together. London dispersion forces. LDFs only. So since it's only London dispersion forces, how would you describe these melting and boiling points? Low. These are also very volatile, not meaning volatile as in unstable, but volatile as in they, because they have very weak intermolecular forces, they're going to escape to the gas phase fairly easily. And for example, sulfur is very smelly. It smells like rotten eggs. That's because those sulfur atoms like to escape fairly easily, and then you can smell them. Okay. Yeah, pretty much the weaker the intermolecular force, the easier it'll escape to the gas phase, and the smellier it'll be. Like gasoline it's all nonpolar, and so it's going to, or most of what's in there is nonpolar, so it's going to be, you're going to smell it. All right, metallic. Metallic. Give me an example. Okay. What? Oh, I thought you said bromine. No. Hydrogen is not a metallic atom. Barium would work. It's radioactive, so I'm not, or no, it's not radioactive, I'm thinking of radium. Okay, how about like brass? It's a metal alloy, but it's all metals, which is why I erase lone atom. Copper, iron, those like typical metals we're thinking of. Okay, gold, aluminum, yep, great. Okay, yes, those are all great examples. So, type of bonding, what holds these things together? What type of bond? It's the name of the category. Metallic. And you learned in Unit 10, because I know you watched all those videos, you learned in Unit 10 that in metallic bonding we have a sea of electrons. that are shared among all of those metal atoms, and that's what holds them together. How would you describe these melting and boiling points? Karthik? Hi. Fairly high, yeah. I mean, some metals you can make melt pretty easily, but you still have to add a lot of heat to them. Most metals at room temperature are a solid. Mercury is like our exception. Other properties of metallic substances is what? They're malleable. Good. What does malleable mean? Bendable. You can hammer into thin sheets. You can make it into different shapes, you know, like jewelry or pots and pans. What else? What? Ductile. Like copper can be drawn into a wire. And I heard somebody say a C word over here. Conductive. No, nobody was cussing at me. They're conductive, meaning that they can conduct electricity and heat. Okay? Ductile is they can be drawn into a wire. I don't know why. It's a duct, not a duck. Okay. Anyway, I'm going to move on now. So, covalent network. What atom did I say we were going to say for covalent network? Carbon. And then another one is silicon, more specifically silicon dioxide, which is glass. Silicon, we're mainly going to talk about silicon dioxide, okay? Glass, because actually what's happening in glass is there's not truly a covalent bond between the silicon and the two oxygen atoms, the way we think of carbon dioxide. What's really happening is you're going to have this huge network, because it is called a covalent network. It's going to be kind of like a lattice, the way ionic bonding occurs. And there's just going to be one silicon for every two oxygen atoms. The oxygen atoms are going to be kind of in between the silicons. Okay? Now with carbon, there are two main ones, and this is pure carbon. We're going to have a two-dimensional lattice and a three-dimensional lattice. And they have different names. Does anyone know what a two-dimensional lattice of pure carbon is called? Most of you have it really close to you. Graphite. Graphite. And I have diagrams later that show you actually how graphite works. Three-dimensional, not a lot of you have this, but diamond. I'm assuming not a lot of you have one of these right now because they are expensive. All right, but yeah, so this is going to be a huge lattice. Okay. So we have lattice network. Typical properties. These are super strong. I'm going to talk about why you can break the graphite, but you're actually not breaking you're not actually breaking the network. I'll explain that in just a little while. Okay? But those are the types of solids, okay? Are you guys good there? Okay, I'm going to the next page. So you don't have to worry about this. This is just saying more stuff, but Two types of solids, amorphous and crystalline. So an amorphous solid is there's disorder in the structures, for example, glass, whereas a crystalline is ordered structures. So our crystalline solids are going to be things like our ionic compounds. There's a very specific order to those solids, okay? All right. So some examples. Here's, a diamond. And then we have sodium chloride. See how that's a very ordered crystalline structure there. And then here is solid water, or ice, if you will. Okay. All right. I know that this diagram, or this is not the best quality, but on your paper it's much better. So you're going to indicate the type of crystal, atomic, lone atom, molecular, metallic, covalent, or ionic. Each of the following would form upon solidification. So really, identify it as covalent network, metallic, lone atom, molecular, or ionic. Lone atom, remember, we're reserving that for non-metals. If it's a metal lone atom, then it'd be metallic, okay? So why don't you go through and identify these. I'm going to pause it while you guys do that. All right, so you've had time to go through this. So, O2, what type of solid? Lone atom. H2S. If you say covalent, do you mean covalent network or do you mean molecular? Molecular. Ag. Metallic. KCl. Ionic. Si. Yes. I said yes. For those of you that don't get it, now it means yes. Before it just meant if. All right. Al2SO43. Neon. What type of solid would neon form? Lone atom. SiO2. NH3. MgO. Good. Just because it contains carbon does not mean it's always a covalent network. It's a covalent network with carbon if it's just carbon. Okay? And silicon, really the only ones are silicon and then silicon dioxide. Okay? So, let me retie my shoe and then we'll talk about some more stuff. All right. So this is just more of the stuff like with what's going on here. All right. Yay. Okay, cool. Don't worry about this. This is showing metallic bonding, the sea of electrons. Yeah, cool. All right, wonderful. This is just kind of going through some stuff. Alloys. There are two types of alloys. Just an FYI. There's an interstitial alloy and a substitutional alloy. So in a substitutional alloy, like what's happening in brass, is like you take pure copper and then some of the zinc or some of the copper is replaced with zinc atoms, and this happens because they're roughly the same size. Okay? An interstitial alloy, which is what's happening in steel here, is you take pure iron and you heat it with carbon, and the carbon atoms, which are significantly smaller than iron, they kind of shove their way in between some of the gaps. Both of these is just ways to make other types of metals that typically will make the metal harder, so therefore more durable. Okay? So that's what's going on there. So just FYI. These are like great multiple choice type questions because it's just definitions and stuff like that. All right, here is carbon. We have a diamond and we have graphite. So a diamond, remember, that's a three-dimensional structure. Look at one of those carbon atoms in that diamond. For example, this one right here. How many carbons is that carbon atom attached to? 4. And this is just a cross section, if you will, or just a portion of the whole diamond structure. Each carbon is sp3 hybridized. So each carbon is forming a tetrahedral formation with the other carbon atoms. Okay? So what types of bonds are there? If it's sp3, the only thing that can happen is sigma bonds. Yeah, we're reviewing some of that Unit 10 stuff. All right, so it's head-to-head it's head-to-head overlap, not sideways overlap, right? In graphite, this one's harder to see, but like, let's look at this carbon atom. How many things is that carbon atom? How many other carbon atoms is that attached to? 3. This is not attached. There are no hydrogens. This is all pure carbon. All right. So this is sp2 hybridized. So in an sp2 hybridized, there's that empty p orbital. That was a horrible drawing of a p orbital, but it's there. It's empty p orbital. And when you have what you end up, bless you, in graphite, you end up with these two-dimensional layers or these two-dimensional sheets that within that sheet is very, very, very strong, but it's weakly bonded to the next sheet because that's where the p orbitals are overlapping. So when you break your pencil lead, when you break the graphite, you're just breaking off a sheet or multiple sheets, if you will. When you're writing with your pencil, you are breaking these weak bonding between. You're breaking those p orbital overlaps, those pi bonds, if you will. Okay? This diagram's a little bit, I find it easier to see it, but that's what's going on there. All right, so you're kind of like taking off a layer at a time when you write with your pencil. But each layer is very, very, very strong, but the layers themselves can separate from other layers easily. What? Sure, it's like skin. I'm thinking like one of those biscuits where you peel off the biscuit layer. All right. I just had one of those last night. All right. This is just FYI, just different things. Semiconductors, you don't really need to know the different types. Just know a semiconductor is made by taking, typically for silicon, but other substances can be used, and you end up doping it with other atoms that increase the conductivity in some way. We're not going to get into all the details, okay? Just know that semiconductors are a great way to, it's made to increase conductivity. All right, again, this is just more FYI. We kind of already went through this. And then the very last thing under this portion is this chart, which is the chart we filled in to begin with, just already filled in. But you learn it better when you write it down yourself, okay? All right, so I'm going to stop the video here and then restart recording for the next one.